coffee cup. You perceive it as solid, still, right?
Mm-hmm. Seems pretty inert.
But what if every single atom in that hand, in that cup, in the air around you, is right now being bombarded by just a continuous stream of particles and energy from the farthest reaches of the universe?
It's a pretty wild idea when you frame it like that.
It really is, isn't it? And it's the core proposition we're diving into today, drawn from an analysis we've been exploring titled The Atom's Cosmic Convergence.
Right, that source material. It puts forward this really powerful image.
Yeah, it says that each atom has a nearly infinite number of light, radiation, electromagnetic, neutrino, etc., coalescing upon its exact location in every moment.
Which, uses language that feels almost poetic, infinite, coalescing, exact location.
Exactly. And the source itself points out, from a physics perspective, those terms need some careful unpacking.
For sure. Infinite isn't mathematical infinity here, and coalescing isn't like things are literally merging into the atom.
Right. So our mission in this deep dive is to get past the poetry, maybe, and explore the stunning scientific reality behind that statement.
What's the actual scale of this cosmic influx atoms experience? What are all these things constantly arriving?
And yeah, what does this unseen bombardment actually do to an atom? And what does it tell us about, well, our connection to the entire universe?
So where do we start? That central idea.
Let's start right there.
Yeah.
Grappling with that nearly infinite number, coalescing upon its exact location. The visual it conjures of an atom as this incredibly busy hub, not some isolated little thing that's crucial.
Okay. So when the source says nearly infinite, it's not talking about like countable infinity.
No, it's emphasizing the vast, just astounding numbers involved and the fact that it's continuous. It never stops. Think staggering quantities arriving constantly.
Okay. Vast numbers, continuous flow, and coalescing.
Yeah, this doesn't mean everything is sort of merging into the atom like raindrops into a puddle.
Yeah, right. It means these particles and energy are arriving at, or maybe interacting with, or sometimes just passing through the volume the atom occupies.
Exactly. Which brings us to exact location. And this is where things get a bit fuzzy, thanks to quantum mechanics.
Ah, right. An atom doesn't really have a single pinpoint spot like a billiard ball does?
Nope. It's electrons, for instance. They exist as probability distributions, those orbitals we learn about.
And you've got things like the Heisenberg Uncertainty Principle, which means you can't simultaneously know its exact position and momentum anyway.
So interactions happen not with some geometric point, but with the atom's nucleus or its fuzzy electron cloud.
So we have this dynamic, probability-defined volume, the atom, which is anything but isolated. It's constantly intersecting with a whole lot of stuff.
So what is this target actually like, at the atomic scale?
Well, an atom, at its heart, is a really dense nucleus, protons and neutrons jammed together, surrounded by a much, much larger diffuse cloud of electrons.
And the scale difference is just incredible, isn't it? An atom is roughly, 10 Iberney meters across?
An angstrom.
Yep, about that. But the nucleus, it's tiny, tiny in comparison. Only about 10 to 10 meters.
Wow. So that means the nucleus is like 10,000 to 100,000 times smaller than the atom itself.
Exactly. Most of the atom's space is really that electron cloud and the vast emptiness between it and the nucleus.
Okay. And this leads us to a really critical concept for understanding this whole barrage idea, the interaction cross-section.
Ah, yes. This is absolutely key because it explains why some particles interact readily while others just sail straight through.
It's not just the atom's physical size, then.
Not at all. The cross-section is the effective area for a specific type of interaction to occur. And crucially, it varies enormously. Depends on the incoming particle's type, its energy, and which part of the atom it might hit the nucleus or the electrons.
So it's like having different sized nets for catching different things. That's a great analogy. A net for butterflies is useless for catching, say, bowling balls and vice versa. The atom's net changes depending on who's arriving.
Okay, so that sets the stage. The atom is this dynamic, mostly empty, probabilistic target with interaction nets that vary. Now let's talk about the deluge itself, the ceaseless barrage.
Right. The source gives us a fascinating breakdown of who's knocking at the door. First up, maybe the most common, electromagnetic radiation. Photons.
Photons. Light, but also much more, right?
Oh, yeah. These are energy packets that span a massive spectrum, from low-energy radio waves all the way up to super high-energy gamma rays. And one of the most stunning examples is the cosmic microwave background, the CMB.
Ah, the relic radiation from the Big Bang. The universe's baby picture.
Exactly. It's the afterglow from about 380,000 years after the universe began, when it finally cooled enough for light to travel freely.
And the numbers are just mind-boggling.
Completely. Roughly 411 cmb photons per cubic centimeter everywhere. Right now, in the space you occupy, every single atom in the universe is constantly bathed in this ancient light.
Wow. But they're relatively low energy, though, aren't they?
They are. They primarily contribute to the universe's background temperature, about 2.7 Kelvin. They typically don't have enough energy to, say, ionize atoms.
But they're a constant presence, a reminder of the universe's origin touching every atom.
Precisely. Then you have more familiar photons, like light from stars.
Our sun, obviously, is a huge source.
Huge! It blasts Earth with something like 10 AH, that's 10 followed by 17 zeros, visible photons per square centimeter every second, just at the top of the atmosphere.
And even distant stars. Their light travels for millions or billions of years to reach atoms right here.
Absolutely. And these interactions can be more significant.
How so?
Well, visible and UV light can excite electrons, bumping them to higher energy levels. Or if they have enough energy, they can knock electrons out entirely. That's the photoelectric effect.
And infrared? Heat radiation?
Right. Infrared light, which is just thermal radiation emitted by anything with a temperature, that causes atoms and molecules to vibrate and rotate. Atoms are constantly absorbing and emitting these thermal photons, trying to stay in thermal equilibrium with their surroundings.
So thermal radiation is part of this constant barrage, too. What about the really high energy end of the spectrum? X-rays and gamma rays.
Yep. You've got X-rays, which can come from incredibly energetic cosmic sources like black holes accreting matter or neutron stars, but also from human-made sources like medical equipment.
And gamma rays, even more energetic.
Even more, from nuclear decay processes or really violent cosmic events like supernovae or gamma ray bursts. These are the high-energy messengers.
And what do they do to atoms?
They can cause deep ionization, knocking out electrons that are tightly bound near the nucleus. They can even, on rare occasions, interact directly with the nucleus itself. They carry a lot of punch.
Okay, so a whole spectrum of photons. But beyond photons, the source talks about perhaps the most elusive members of the barrage, neutrinos.
Ah, the ghost particles. That's a good name for them.
Because they barely interact with anything.
Exactly. They're elementary particles, fundamental building blocks, and they interact primarily through the weak nuclear force and gravity, which means, for the most part, they just don't see normal matter.
But their numbers. The source mentions those are immense.
Absolutely staggering. Take solar neutrinos, produced by nuclear fusion deep inside the sun's core. Get this. Something like 65 billion solar neutrinos pass through every single square centimeter of your body, your desk, the Earth, every single second.
65 billion per centimeter squared per second. Unseen, unfelt.
Unseen, unfelt. And that's just the ones from the sun. There are also atmospheric neutrinos created when cosmic rays hit our atmosphere. There are geoneutrinos from radioactive decay inside the Earth itself. There's a cosmic neutrino background like the CMB, but for neutrinos from the very early universe. And astrophysical neutrinos from distant exploding stars or active galaxies.
So astronomical numbers.
Yeah.
But you mentioned that tiny interaction cross-section earlier. That applies big time here.
Big time. This is where the contrast is just fascinating. Despite their sheer abundance, the probability of any single neutrino interacting with any single atom is, well, vanishingly small, almost zero.
So the vast majority just pass straight through.
Straight through. Straight through you, straight through the entire planet Earth, like it wasn't even there.
We do detect them, right?
We do, but it takes huge detectors, often deep underground, to shield from other particles filled with tons of material, just waiting patiently for that incredibly rare interaction to happen. It's proof they exist and carry information, but on an atom-by-atom basis, their effect is negligible.
Okay, neutrinos? Numerous, but nearly non-interacting. What about the more substantial visitors? The source mentioned cosmic rays.
Right. Cosmic rays, these are different. They are high-energy particles, mostly atomic nuclei themselves, that originate from outside our solar system.
Like protons and helium nuclei.
Exactly. The source breakdown is about 89% protons, hydrogen nuclei, about 10% alpha particles, helium nuclei, and then a small fraction of heavier atomic nuclei, plus some electrons, positrons, and other exotic particles like muons that get created when these primary cosmic rays smash into Earth's atmosphere.
And they're coming from?
Supernova explosions, active galactic nuclei. Basically, places in the universe that act as powerful particle accelerators, flinging these particles out at near light speed.
Their numbers, the flux, is it high like neutrinos?
No, much, much lower than CMB photons or solar neutrinos. But, and this is the key difference, each individual cosmic ray can carry enormous energy, way more than typical photons or neutrinos.
So when they do hit an atom, they make their presence felt.
Oh yes, they can be quite disruptive. They have enough energy to easily ionize atoms, knock them out of their place in a crystal lattice. They can even cause spallation, which means they literally break atomic nuclei apart or induce other nuclear reactions.
So they're a significant source of background radiation.
Definitely. And they can cause damage to materials, electronics, even living tissue, which is a major concern for space travel.
Okay, disruptive cosmic rays. One more thing the source mentioned. Gravitational waves. How do they fit into this barrage? They aren't particles in the same way.
No, they're fundamentally different. They are ripples in the fabric of space-time itself, generated by colossal events like merging black holes or neutron stars.
And they pass through everything too, right?
They do. They stretch and squeeze space itself as they pass, affecting everything within it. But the key point the source makes is that the direct effect on the structure of a single atom is extraordinarily tiny.
So way below the energy scales of typical atomic interactions.
Far, far below. So while gravitational waves are constantly washing over us, they aren't coalescing or interacting with the atom's components in the same way a photon or a cosmic ray does. It's a different kind of universal influence, a distortion of the stage rather than a direct hit by another actor.
Okay, wow. So the barrage is this unbelievable mix. Ancient, low-energy photons from the CMB, constant thermal radiation, light and high-energy photons from stars and violent cosmic events, those ghostly, barely there neutrinos in the billions, energetic, disruptive cosmic rays, and these subtle stretches of space-time from gravitational waves.
That's a pretty good summary of the constant cosmic weather every atom experiences.
Given all this influx, what does the source say are the actual consequences for the atom? Does it fundamentally change it?
Well, it means an atom is almost never truly in a quiet, isolated ground state. It's typically in a state of dynamic equilibrium. It's constantly receiving energy and particles, and sometimes responding to them, trying to stay balanced with its environment.
So it's not just sitting there statically. It's vibrating, absorbing, emitting, getting nudged.
Exactly. We mentioned excitation energetic photons or particles can bump an electron temporarily to a higher energy level.
Or ionization, knocking the electron out completely.
Right, which changes the atom's charge and how it interacts chemically.
And you also mentioned earlier that even just absorbing or emitting a photon transfers a tiny bit of momentum. Does that add up?
It does. It causes a tiny recoil, contributing to the atom's overall motion. Think of the random jiggling of particles we see as Brownian motion, or the cumulative effect of light pressure from intense sources. It's a real physical push.
But didn't we also establish that for many particles the impact is basically zero?
We did, and that's crucial too. The source notes that for particles like neutrinos, or very low-energy photons, the interaction probability is just so low, or the energy they transfer is so minimal, that they typically have no discernible effect.
The atom is essentially transparent to them, as the source puts it.
Exactly. They just pass right through without leaving a mark, most of the time.
But when interactions do happen, like absorbing or emitting a photon, it's not a smooth process.
No, it's quantized. It happens in discrete steps, those famous quantum jumps. The atom abruptly transitions between specific allowed energy states by absorbing or emitting a precise amount of energy, a quantum.
And maybe the most profound consequence the source points out. These incoming particles, they carry information.
This is really where it gets mind-blowing.
Yes.
The light an atom absorbs or emits, the particles it interacts with, they aren't just random noise. They carry the fingerprints of their origin.
How so?
Well, studying the specific wavelengths of light, the spectra coming from atoms in distant galaxies, tells astronomers about star formation, the chemical composition of nebulae, the expansion of the universe itself.
And the CMB photons.
They are direct messengers from the cosmos's infancy, telling us about conditions just after the Big Bang.
And neutrinos.
They give us a window into the nuclear furnaces inside stars, like our sun, or the catastrophic core collapse of a supernova processes we could never see directly with light. Every interaction, or even the pattern of non-interactions, is a piece of cosmic data arriving at the atom.
So bringing all this back together, the analysis really reinforces that statement. No atom is an island.
It really does. It captures the essence perfectly. Every single atom is described as being intimately and perpetually connected to the entire universe around it.
Constantly being touched, as you said, and informed by signals from across vast distances of space and incredible stretches of time.
Think about it again. Those CMB photons hitting an atom in your fingertip right now link it directly to a moment less than 500,000 years after the Big Bang.
Starlight arriving now might have started its journey when dinosaurs roamed the Earth, connecting that atom to fusion happening light years away.
And those billions of neutrinos whispering through it carry immediate news from the heart of our sun, or maybe from a supernova that exploded galaxies away millennia ago.
So the initial idea of coalescence, while needing that careful scientific definition, it really does beautifully capture this constant, incredibly dense influx and this fundamental, unavoidable connection.
It does. It forces us to shift our perspective. The atom isn't just a static building block. It's a dynamic nexus point, a tiny antenna constantly receiving signals from the entire cosmos.
This deep dive has really pulled back the curtain on the unseen reality of atoms. The scientific picture behind that poetic phrase is just stunning, this unceasing, incredibly dense, and wildly diverse bombardment by cosmic particles and radiation.
Atoms aren't just inert little components. They are, as the source puts it so well, in a state of dynamic perpetual interaction with the energetic tapestry of the universe.
Which leaves us, and you, the listener, with this final thought to consider. As you sit here listening, the atoms making up your body, the air you breathe, the objects around you are, in this very instant, being pierced by billions upon billions of neutrinos from the sun.
Bathed in relic radiation from the literal dawn of creation.
Subtly jostled by light that began its journey millions, maybe billions of years ago.
And occasionally getting zapped by a high-energy cosmic ray that traveled across galaxies.
So what is this constant, unseen, cosmic conversation happening inside everything around you and within you mean for how we understand what it is to be here right now?
Yeah.
Connected intrinsically to everything out there.